In electrophilic aromatic substitution, the objective is to add incoming groups to the substituted benzene ring. Now, if the benzene ring is unsubstituted, it's pretty straightforward. We just add the incoming group. But if it's monosubstituted, disubstituted, or even trisubstituted at times, then the groups that are already present on the ring influence the positions, right, at which the substitution will take place for those groups that are being added to the ring. So let's walk through this problem. So we see here we have 3 different reactions that are taking place, but we don't even start off with the unsubstituted benzene. We start off with methylbenzene, toluene, and we see here we have a methyl group. And so we need to think about the influence of this methyl group on the benzene ring in terms of the addition of these groups, right, in the presence of these reagents. So a methyl group is an R group, okay? R groups, alpha groups, in general are activators. They're activators of the benzene ring. Activators means they donate electrons to the ring. So if you think about induction, the fact that you have a carbon here and a carbon here, then of course there's a greater electron density in the benzene ring. So it will have a strong pull, okay, on the carbon, and so we say that there's a stronger affinity of these electrons to the ring. So through induction, we can say electrons are being donated to the ring. So they're activators. And in general, activators are ortho 1,2 or para 1,4 directors. So we have the ortho-para director, which is the methyl group. So we know that in the first reaction, we should see substitution at either ortho positions. We have 2, it's a symmetrical compound. So, compound. So we have here the ortho positions as well as the para position. Okay, so that's what we have. So what exactly are we adding to this ring? Even though it's a substitution, I say add, but remember this is electrophilic aromatic substitution. We have a bromine. How do I know that? Here's bromine, Br2, in the presence of its catalyst. It's an iron catalyst. So generally for EAS, which is electrophilic aromatic substitution, the reagents are at the top and we put the catalysts below. So we're not adding iron or anything crazy to the ring, we're just adding bromine. We're also only adding 1 atom of bromine, okay? It's a single molecule substitution. Remember that what you're doing in EAS, right, is you have, this is benzene in its native state. And listen, look, I've drawn the alternative version, but it has 6 hydrogen atoms because the molecular formula for benzene is C6H6. And so essentially what we do in electrophilic aromatic substitution is we substitute these hydrogen atoms. That's what we're doing, okay? So it's a substitution mechanism. This is why we replace 1 hydrogen atom with 1 bromine atom, okay? Now, I'm stressing this because when we look at other reagents like nitric acid in the presence of sulfuric acid, we add 1 group, but the point is we form 1 bond. We form 1 new bond per reaction. That's what I'm trying to stress. So when you have Br2, okay, you're going to break the bond here and 1 will go to the ring. You won't do it twice, okay? We do 1 reaction per cycle. And so we add 1 new bond to the ring, okay? So it's substitution. All right, so let's see. We know we're going to have the bromination shown here. The second reaction will be nitration. This is nitric acid in the presence of sulfuric acid. So we know that we're going to add what's called the nitro group. We create nitrobenzene by using nitric acid in the presence of a strong catalyst such as sulfuric acid, acid catalyst. And the nitro group is nitrogen dioxide, NO2. Now the third reagent we have is potassium permanganate, a very potent, strong oxidizing agent. But potassium permanganate is not a reagent that we use on benzene rings. And you actually had a little bit of a clue here. In the alternative representation of benzene, we actually show 3 individual double bonds. But benzene does not obey the rules or follow normal double bond alkene chemistry, right? Alkenes are compounds that have double bonds, but benzene is not an alkene. In fact, the reason we draw benzene this way with the circle is to remind you that what you have is not essentially 3 individual double bonds, but a pi system where electrons are actually shared across or throughout the entire ring, okay? And that creates this type of stability in the molecule, the compound, benzene, which makes it inert to the normal reagents that we use for alkene or double bond chemistry. So this reagent won't do anything to the ring itself. Keep that in mind. It doesn't mean it can't do something to the side chains on the ring. All right, so now we can begin. So I start off with a monosubstituted benzene with a methyl group, and I have 2 positions that are vacant. I have the ortho, which is the 1,2. It's a symmetrical compound that's available on both sides, and the para. So I can actually form both products, okay? And in nature, you will have both products formed. However, one is favored more than the other. And in this case, it's not the one that's most intuitive that's favored. However, on multiple choice questions, unless you're asked to identify multiple products, you only need to find one correct product. And this is multiple choice, so you only need to walk yourself through and find the sole or only correct product. So you see here we can have the ortho substitution. This one is favored in nature about 60 to 70% actually over the para product, which is here. It seems more intuitive that it would be para because of steric hindrance, right? Why would you place two groups adjacent next to one another in a ring when you could put them 1, 2, 3, 4, right, positions apart? But this is the one that's favored in nature for reasons we won't go into, and we really don't know why, but we have theories. So this is the one that's favored. However, we have to walk through both because we're trying to find the correct response, and we're not guaranteed that this will be the one that leads us to that path. All right, so now we have this di-substituted benzene. We've added a bromine group. The next situation or the next reaction is to add the nitro, okay? So we have nitric acid in the presence of sulfuric acid, and we want to add a nitro group, NO2. So let's look at this. I have a methyl group. It still behaves, let's use another color, as an orthopara director. So as an orthopara director, the methyl group can influence substitution here, here, or here. And then I have a bromine group, and it also behaves as an orthopara director, so it can influence substitution here, okay, here, or 1, 2, 3, or here. Okay, so I can actually add my nitro group anywhere. Let's come over here and do the same thing. Now I actually have an interesting situation. These two groups are para to one another, so I only have ortho substitution vacancies. Okay, so how do I decide what happens? Sometimes you should also look at the incoming group. Now, I just mentioned to you that the bromine is an orthopara director. The halogen, which we abbreviate with an X, they're actually deactivators. They can be well, technically they can be activators or deactivators, but generally we refer to the halogen as a deactivator. Halogens are actually a little bit special, even though they withdraw electrons from the ring, because think about it, halogens belong to group 7 of the periodic table. They're much more electronegative than carbon, so they'll pull electrons away. However, when it comes to substitution, they are actually ortho and para directors. Generally, deactivators will be meta directors. So something like a nitro group will be a 1,3 director, right? But the bromine, even though it's also withdrawing, is an orthopara director. So if I wanted to place a nitro group on this compound here, the most logical place for me to place it or to put it would be where, right? Would I put it here? Or would I put it here? I can put it anywhere. Now, another thing in terms of hindrance because of size, you're not going to put 1, 2, 3 compounds next to one another or 3 groups. So this one is not going to happen. These two are occupied. I'm not going to put 3 next to one another, so that one is no longer valid. So now I'm left with this. It's actually this product that will form, okay? Because we want to space the two deactivating groups as far apart as possible, okay? And now also note that this nitro group is now 1, 2, 3 away from the methyl group. It's now meta. So the nitro group is 1, 2, 3 meta to the methyl group. Why am I stressing this? The methyl group is more reactive than the bromine group. So that's another thing you have to commit to memory, is the increase in order of reactivity. So our groups are more reactive than halogens. So now we have a very good situation. The two deactivating groups are further as far apart as possible. The incoming group is now meta to the more activated group between the methyl group and the bromine, and it's also para to the bromine, which is good. Okay, so that's actually the product that will form. On this side, we have to make a decision. Are we going to put the incoming nitro group ortho to bromine or ortho to the methyl group? As I said before, the methyl group is a greater or stronger activator, or it's just more reactive than the halogen. So we'll actually put the nitro group here in the ortho position. Okay, and that's it. All right, Now, I've already put a box around this one to stress that this is the one that's favored in nature. All right, now, but notice that I'm walking you through the other products as well. Now, the last step will be the oxidation. As I mentioned to you before, benzene itself, and I've actually drew it here this way, is inert, okay, to oxidation by oxidizing agents such as potassium permanganate. So the reason we have it here is it's not that you're not going to have a reaction, it's the side chains. So in electrophilic aromatic substitution, you need to remember that we reduce nitro groups to NH2 and we oxidize alkyl groups, R groups, okay, to carboxylic acids. That's the general rule. So we use this oxidizing agent to create a carboxylic acid. That's what we do. So we get C double bond OH, COOH. And so that's essentially it. We're going to change the methyl groups to that, to carboxylic acids. So now we have created acids. Okay. Okay. And the only difference between the two products, as you can see, is here the acid is adjacent or ortho to the bromine, while here it's adjacent or ortho to the nitro group. So these are the two products that are formed. However, the favorite product would be this one because in nature, it is the ortho product that is actually dominant to the para product when we take methylbenzene and we brominate it in the presence of a catalyst, iron catalyst. And then we add the nitro group, of course. Remember that both the methyl group and the halogen are ortho para directors, even though the halogen is a deactivator. And finally, potassium permanganate can be used to oxidize side chains on the benzene ring, but it doesn't do anything to the benzene ring. So either of these two would be the correct response. And since it's multiple choice, you only had to identify one of them.